Hey there, welcome to another Let's Code. Corey here with MindfulBit. Today we're going to be coding a binary tree in Java. Binary tree is one of the classic data structures usually taught when anyone learns computer science. I'm going to leave it up to you to go research the theory behind the binary tree. This video is pretty much strictly to show what it might look like when coded in Java. So without further ado, let's dive right in. We're going to come into Intellij, which Intellij is an IDE that I use. You may be using Eclipse or some other IDE, that's perfectly fine. I do recommend giving Intellij a try though, because um, it's been nice switching from Eclipse to Intellij. There's a lot of useful hotkeys, and it's just been easier to navigate and test, as far as I can tell, with Intellij. So I've been using it for about 5 years now. I used Eclipse prior to that, and I would definitely choose Intellij over Eclipse. So let's go ahead and create a new package here under our data structures directory. We're going to name this package binary tree. And the first class we're going to create is our node class. So let's go ahead and create a new Java class. We're going to name it node. So we're going to implement the linked list sort of node implementation of a binary tree. So there are multiple ways you can implement a binary tree. You can use linked list, you can use arrays. There are other more creative ways you can represent it, but node to me makes the most sense, and to me will probably be a little bit easier to follow along with. So what we want here is to have a private left member that's a node. So each binary tree node will have a left child and a right child and a parent. So each node will have siblings, and each node will have a parent. And we're going to give getters and setters to all of those methods. Okay, so this is the very generic node class: left child, right child, and a parent child. And let's go ahead and create our binary tree class. This guy's going to have a root node. Every tree has to have a root. Actually, I think we'll leave this guy empty for now, and we won't do the root implementation. Let's just play that out and see how it works out. For a binary tree, though, we're going to have public void insert, and we're going to be inserting nodes, and we might have public void remove, so we might be removing nodes here. Let's do our insert method. So what we want to do is let's go ahead and set a root. So we'll have private node root. And the reason we need a root is we need to know where to start from. So it's going to initially be empty, but we'll set it to our very first value. So if root is null, we want to go ahead and set our root to the new value. Else, all right, and here's we basically forgot that a node can capture data. And when we're creating a binary tree, all data that is less than the current node will go to the left. Data that is greater than the value of the current node will go to the right. So we need to be able to represent that data. And we'll make that an integer for this particular implementation. There might be implementations where it's a string or something a little bit more complex. In that case, you would need your own comparators to decide whether or not something is less than or greater than. It's a lot easier when it's an integer because we all intuitively understand this number is less than this number. So that's why I chose data there. And let's go ahead and create a node constructor that takes in the data. Okay. Let's also create a constructor that takes in parent and data. We might use that. And I'm doing this video, I haven't coded a binary tree in a while. I like to do these while they're fresh on my mind so that when I run into things that I don't remember, I can be honest about that. Because a lot of times in these videos, you get a very sanitized version of someone's thought process. So it makes you feel like, oh, I should know that intuitively. But a lot of this stuff, you know, it's trial and error. You play with it and you learn it. So when you're watching someone teach these things on the YouTube videos, a lot of times you see this very professional, clean-cut implementation, which leads you to believe that it's you that's the one that doesn't understand, which that's not the case. So the reason I'm doing it this way is just so you get an insight into how my brain works, and also it's more authentic. I've been coding for 15 years, so if I don't know these things off the top of my head, I wouldn't expect you to either. So now we're going to say if we're going to set the current node to the root. Okay. And we're going to say if current dot get left not equal to null, and in dot get data is less than current dot get data. So basically what we're doing here is we're saying, okay, if the current node has a left child and that left child has a data value that is less than the value that we're putting in, or if my data value that I'm passing in is less than the current, well, we're going to set current equal to current dot get left. Else current equals, else if current dot get right not equal to null, current equals current dot get right. Okay, so we're going to go left if the value is less, we're going to go right if the value is greater. And we're going to keep doing this until current is equal to null. While current is not equal to null, I want to keep doing this. Which means now that we have this while loop, we don't need to check if it's not equal to null because we'll know that it's not. So that simplifies our code quite a bit. So once we get out of this while loop, once we get out of this while loop, I'm thinking out loud here, so we'll be at a leaf node, a null leaf node, and we'll have the parent. I think what I can do here is say if current equals null, think I'll have this check in each one of these if-else statements. If current is null and we went left, well, we know that we want to set current dot get parent dot set left to n. So that means if we got to the leaf, current equals null, current dot get parent dot set right is n. So we'll try that out. We'll test it to see if it works, and we'll do a print to see what the actual values look like. So let's do a pre-order traversal here. Public void pre-order takes in a node and this is going to print the pre-order is current left right. So it's going to print the current, then we're going to run pre-order on left, pre-order on right. This out dot print line in dot get data. There's current. We're going to call pre-order on in dot get left and pre-order on in dot get right. If n equals null, this is our base case, return. Okay. So now let's just create our main method and play around with our code. We want to create a new binary tree. We'll call it B tree. And we're going to insert some values. We'll insert a value of 3. Then we'll insert a value of 17. Then we'll insert a value of 1. And then we'll run it with our pre-order. We'll pass the root in. Okay. So we're going to add 3 numbers. We should have a 3, a 1 to the left of the 3, 17 to the right of the 3. Here we go. And you can see we received a null pointer exception, so let's dive into that right here at current.getParent.setRight. So current is null here, but the parent is, the parent's probably null. Let's set a debug. We're going to run this in debug mode and see at what point this actually, oh, obviously. So you see the code mistake. If current equals null, then I'm trying to get parent. That doesn't make sense because I can't access the parent from a null node. So let's revisit that logic. If current.getLeft equals null, then current.setLeft. If current.getRight equals null, then current.setRight. There we go. So if, and then we're going to do else current.get left, else current equals current.get right. Okay, so I think this should work. If the current.getLeft is null, then that means it doesn't have a left child, so we'll set the left child to the one we're inserting. Otherwise, we'll just go ahead and set current equal to the left. If the right child is null, we'll set the right child to n. Otherwise, we'll set current to the right child. And we also need to iterate through. So we'll say while actually we'll return after we do the set, because we should always hit these cases. Okay. Let's run it again, see what happens. $317. That's exactly what I would have expected. The pre-order traversal prints the top, then the left, then the right. So if I were to insert another object here, btree.insert new node, we'll do 15. We'll start at 3. It'll say, okay, 15 is greater than 3. It'll go to the right. And then it'll say 15 is less than 17. So 15 will go to the left of 17. So now we should get 317. We should have seen 31715, but we did not. So let's put a breakpoint here and dive in and see where that's getting inserted. So we're going to insert our new node with 15. We'll step into it, not over it. So let's step in. Step out of this. Step in again. Root does not equal null. Current is root. Current.getData. If current.getRight, so let's see what current is. Current's right, value is 17, that's great. So now current is going to be 17. Okay, so as you can see, we're not iterating through for this case. Yeah, so let's do while current is not equal to null. So this while loop should keep us going, and it'll allow us to iterate through the tree. And then when we do the insert, we'll return. That should take care of it. Let's run it initially. We'll see if we get the output we expect. There we go. So let's add a couple more. Let's add in a 2. So 2 should go to the left of the root. So we should see what's printed is 3, 1, 2, 17, 15. Yep, 3, 1, 2, 17, 15. All right, so looks like our basic insert. I think we'll just do insert for now and not worry about remove. Typically, you don't, when you're creating a binary tree or a binary search tree, you don't really want to remove things. Let's say you get an array of unsorted integers and you want to be able to find out if there's a particular number in there, and that operation the search will be happening multiple times. So you'll basically build out the binary tree once, and then you'll create a method that will tell you whether or not this value is present. So let's create that. Public void search, and we're going to search for an integer value. We're going to say if root equals null, then return false. So the return type is going to be a Boolean. It doesn't exist if there's nothing in the tree. Else, we'll set current equal to root. If current.getData equals value, return true. Okay. If value is less than current.getData, current equals current.getLeft. Else current equals current.getRight. And we're going to do this while current is not equal to null. So then if current equals null, that means we made it all the way through the tree and we did not find our value, so we can return false here. Okay, so now this is our search method. We should be able to say sout btree.search 9. Okay, so this should search for the value 9 in our binary tree and false. But let's say we want to search for the value 15. Let's see what we get here. You see we get a value of true. So the beauty of this is it's log-in. So it's search and log-in time, which means every time you move through the tree, you split the entire number of items you have to search by 2. Just because it's a binary tree and everything is logarithmic as you go down. So it goes 1, 2, 4. So it really allows you an efficient search. So the binary tree search algorithm, binary search, is typically pretty efficient. So I think we'll stop there with binary tree implementation. Do play around with it. There are some other methods that typically go into the binary tree interface, like returning siblings, returning parents, and that sort of thing. But once again, I think we'll stop there for today. And if you do have any questions, please comment on the video and let me know if you're interested in coaching. I do offer soft skills coaching for communication, basically just to allow developers to be able to communicate more efficiently, leaving your ego at the door. How do you talk to someone authentically, openly, efficiently, and effectively? So check out mindfulbit.com, and I hope to see you on the next video. Thank you. Bye-bye.